Thanks for the opportunity. It's a great honor and a pleasure to come and visit Chad. Very lucky to have sneaked onto the topology seminar. I'll describe some work that we've been going on for quite a long time. It's taken us quite a while. There's four of us working on it, and sort of I collaborate the most with this person here, Jamie Vicary, and that's why I wrote his name first, because it's not because I think he is because he is, but anyway. Okay. So I'm first of all just going to tell you a little bit of the timeline. I know some of you have heard all the story before, but let me just say it so that you know the basic context of what this whole thing is all about. So there's a sort of story about how mathematical physics or theoretical physics re-entered mainstream geometry, and one narrative is that sort of idea met Witten in 1977, and that certainly was a big event, and changed the face of a lot of stuff that he discovered over the years. So Jones came up with the Jones polynomial invariant of knots in 83. Okay. Knot invariants, as far as I understand it, could be right, sort of have been relatively dormant for quite a while until then. Right? There'd been the Alexander polynomial, and then a number of years there wasn't at least polynomial invariance. So this came a bit out of the blue by operator algebras, and then Tia challenged Witten to come up with the quantum field theory explanation for it, and Witten said okay, and the next morning he gave a talk on that at the conference, and he explained it geometrically as, so you got this weird polynomial that we're going to assign to a knot. It's a polynomial with q, or square root of q, and how are we going to calculate it? You take the knot, you consider all the SU2 valued connections on the manifold, and for each such connection we can calculate the holonomy of the connection around the knot. So that's a very geometric thing, so parallel transport around the knot, and each different connection, so we take the trace of that, gives us a number, each different connection gives us a different number, and we add up all those numbers over all the connections. So that's a bit strange, of course, because we're doing a path interval there. You're integrating over a huge space, and that's very dodgy. But nevertheless, where does q enter? Q is equal to e to the 2 pi I over k plus 2. So we identified the q as being some kind of a root of unity, or at least related to 1. And there's a weight factor that we weight each connection by, and that's the Chern-Simons action of the connection. Okay. So it's a sort of a beautiful geometric statement, but unfortunately requires a path interval to make precise. But Witten was able to calculate with this, and you know he won't go to Fields Medal for that. And Tia then wondered what on earth is this thing, and tried to formulate it mathematically, and sort of wrote down axioms, mathematical axioms for what a topological quantum field theory is. Seagull then took Tia's axioms and tried to reformulate them, and he said, hold on, this should be some kind of, we can formulate this categorically, and he said once the sort of dust has settled, what you're left with is a functor from cobordism category to category of vector spaces. So in this case, for Chern-Simons theory, it would be a three-dimensional theory. So to a closed surface, we need to assign a vector space. And to a bordism between surfaces, say there's a bordism which goes from this surface to that surface. So I've got my colors here. Gets assigned a linear map. And this is factorial. It respects the various operations in the category, like if I were to take disjoint union on this side, it should go into tensor product on the vector space side, things like that. Okay. the subscript 2, 3 there is saying that the objects of my category are two-dimensional manifolds and the morphisms are three-dimensional cobordisms. Okay, and that was how things sort of stood for quite a long time. And then in the 90s, people started wondering, okay, so in these theories, then we can calculate what they do on 3D manifolds and on 2D manifolds, but the natural question to ask is, what if you go further on down? What does it make sense to ask, does the theory assign something to a one-dimensional manifold? What about to a zero-dimensional manifold? Yeah. And there's various reasons why you might want to know that. And that was, in this narrative that I'm sketching at least, when Byers and Dolan sort of came into the scene. And I wrote a influential paper called High-Dimensional Algebra and Topological Quantum Field Theory, outlining a far-reaching program which had a lot of influence on sort of the way the subject is looked at. Okay, so they made 4 big statements in that paper, and I'll outline 3 of them. The first, so this is sort of like a dream for how the theory is supposed to work out at the end of the day. So the first one is the tangle hypothesis, and basically saying that the n category of frame n tangles n plus k dimensions, n plus k equivalent to the free weak k top humanoidal n category of jewels in one object. So a huge thing to swallow there, but what I want you to keep in mind there is that we've got some geometric category, some geometric thing, namely in this case frame tangles in n plus k dimensions. So for example, if n equals 1 and k equals 2, then we're talking about tangles in 3 dimensions. And you can consider a tangle as a bunch of strands between 2 planes, and they could wrap around each other. You can compose them by gluing top and bottom to each other. A frame tangle means we have a normal trivialization of a normal bundle of each strand, so they're really ribbons, and these form a category, and they're saying that that geometric category is actually a free sort of algebraic category by a free category with jewels in one object. So if we could make sense of the notion of a free k-tuple monoidal n category with jewels in one object, that's some kind of algebraic thing, you could write it down with equations. Then we have a complete dictionary here between geometry and algebra. Okay, higher dimensional algebra. That's why the paper was called that. Okay, now you might ask, okay, what happens if I take k to infinity? So k is the codimension in which these tangles are living.
Why is it a hypothesis instead of like a conjecture?
Because there's so much stuff that you have to make sense of here.
I see.
That's the problem on the categorical side. So the notion, basically, at the time, people were, I mean, you're talking higher categories. People, a 2 category was a state of the art then.
So hypothesis is a conjecture with conjectural definitions.
Okay.
Does that sound right?
Thanks. Says it very nicely. But I want to draw the analogy with Grothendieck homotopy hypothesis, because that's also exactly the same nature. So that's a statement about what the category of homotopy or of topological spaces up to homotopy should look like, and you can then go ahead and define what that is. And so Grothendieck says that topological spaces up to homotopy is the same thing as an infinity groupoid. Topological spaces are the same as infinity groupoids. That's Grothendieck's big dream. And you go and define an infinity groupoid to be a topological space, in which case the theorem is true by definition. Or you can, we could do the same thing here, but then it would be sort of empty. So that's why another reason why it's called a hypothesis is because it's sort of trying to frame the direction in which you want things to go. The cobordism hypothesis here we take k to infinity, so we can think of these as being abstract sort of manifolds, abstract tangles. And now the statement is that the frame borders an n category. So that means that we take objects or points morphisms of framed one manifolds, 2 morphisms of framed cobordisms between those one manifolds, 3 morphisms of framed 3 cobordisms between those 2 manifolds, and so on, up to n. And that beautiful geometric category is the free stable n category of duals in one object. Okay, so again, beautiful dictionary between geometry, of manifolds and algebra. So if we could only know what this was, the free stable n category of duals in one object, we could just only write down some equations for that, then we'd learn a tremendous amount about differential manifolds. And the fourth thing that they did was they said, okay, what is a TQ of T? So that's answering the question on the previous slide of those question marks. They said, okay, what we think it is it's just a monoidal n functor, which goes from this borders in n category into the n category of Hilbert spaces, preserving all levels of duality. So there's, again, a whole bunch of n's and stuff that might sort of make your eyes glaze over. But what I wanted to get at here is that they were saying that an extended TQFT is a representation of that thing, that algebraic thing, which has as objects points, as morphisms, frame cobordisms between the points, and so on, up to n, into some kind of linear space, which also has things and things up to n. Okay, so we're doing some representation theory of cobordisms. So in this paradigm, you can fill in what Bayes and Dolan said, what should come in here. A closed one manifold should be assigned a linear category. A linear category must mean an ordinary category where the Hom sets are vector spaces. And a point should be assigned a linear 2 category. So that means, yeah, where the functors now have Hom sets which are vector spaces. Okay. So note this weird thing that's going on. As the manifolds get more complicated, the algebraic invariants get simpler. As the manifolds get simpler, the algebraic invariants get more complicated.
So what if you make the list of red things keep going down?
Can you?
Left-hand side?
You can actually go down here, and there's a thing you can get to the true false. Yes, but there's some people who sort of philosophize about that. And, I mean, there's also that issue. I mean, there's, like, you know, the whole philosophy about the field of one element sort of comes in here as well. But that's a little bit above my pay level.
So what about the sort of dual question? I mean, what happens, like, is there some reason you can't do this for 4?
Because this is a 3-dimensional extended theory. So Bayes and Dolan said what an n-dimensional theory is. So this is a 3-dimensional theory of numbers at the top level and go down. Okay.
So if you could maybe do it with 4, and then you could go farther.
Yeah, that would be a 4-dimensional theory.
Okay.
Yeah.
So again, what's the linear category? What would it be?
I'll come back to that shortly, but a linear category is just very down to earth. It's just a category in which the Hom sets are vector spaces, finite dimensional vector spaces. I've dumbed it down slightly there, not much. And then, since then, there was a whole lot of sort of developments. All of them a little bit disparate. Still hasn't emerged a fully satisfactory unifying picture. And I'm sure you've heard of a bunch of these buzzwords. Many of them I don't understand at all. So, quite a big thing happened in 2009 when Jacob Lurie sort of defined all those categorical stuff should mean, using his version of what higher category theory is all about, and actually outlined a proof of the cobordism hypothesis. So it's for me extremely difficult to read, but the geometric input here that he used was that the space of framed Morse functions on a manifold is contractible. So sort of almost was a theorem of Igusa, and Lurie then completed that. Igusa showed that it was highly connected, and Lurie extended that to show that it was contractible. And this, we're now in sort of the fallout of that, trying to piece together what on earth he did. That's where I am. Okay. So let's get down to earth now and just talk about my talk. So I'm just going to be talking about two categories here. So just very roughly, a two category consists of objects, which we'll draw as things like that, together with one morphisms, and two morphisms, which we will draw like that. Okay. You can compose the one morphisms in a one-dimensional way, just like you can compose arrows in a category. You can also compose the two morphisms. Now you can compose them in two ways, vertically and horizontally. Okay, this is higher dimensional algebra here, two-dimensional algebra. And there is one condition that this must satisfy. It must satisfy that if you compose two morphisms like this, and then like that, that's the same as going across and then down. There's a natural condition you can write down. And that's the requirement to form a two category. Okay, they must satisfy some coherence laws like the one I just mentioned. So some examples of two categories to think about. So top is the two categories. Objects are topological spaces. Whose morphisms are continuous maps. Two morphisms are must be two continuous maps. In cats, the objects are categories, morphisms are functors. Two morphisms are natural transformations. Lim-cat, the objects are complete C-linear categories. I'm just dealing with the complex numbers. So that's a category where the Hom sets are finite dimensional complex vector spaces. Complete in the categorical sense basically means that all your limits and co-limits that you want must exist. Okay. Morphisms are linear functors, meaning they're linear at the level of Hom sets, and two morphisms are natural transformations. Alg is another nice two category. Objects are algebras. One morphism are bound modules, because you can compose bound modules by tensor. Two morphisms are bound module homomorphisms.
By module, multiplying both sides by the algebra.
If I've got an AB bound module M and a BC bound module N, I can compose them together to get an AC bound module by tensor. And just think of any of your favorite structures that has morphisms between the morphisms. Generally, it'll form a two category. Chain complexes is another one. Right? Objects are chain complexes, morphisms are maps of chain complexes. Two morphisms are homomorphic maps of chain complexes. I shouldn't stop there. I should go on to infinity, and that's what Lurie does. Right? But I'm just dealing with the old-fashioned way of doing it. So, the oriented 1, 2, 3 bordism 2 category, board OR for oriented 1, 2, 3, the bottom is a subscript, is defined as follows. So an object is a closed oriented one manifold. Like, basically it just means it's a collection of circles. A one morphism from A to B is a bordism from A to B. Yeah. So it means a compact oriented two manifold whose boundary is equipped with explicit parameterizations to A bar of disjoint union B. So yeah, time is running from bottom to top, and this is a bordism from A to B. It's a one morphism in our two categories. A two morphism would then go between two-dimensional bordisms. So two morphisms is a three-dimensional bordism from sigma to sigma prime. Okay. For example, here's a two-dimensional bordism from the circle to the circle, and here's another one. And this is a three-dimensional bordism going from this bordism to that one. Okay. You can visualize it with the help of a Morse function, and you can get a movie of it. Okay. So you compose the one morphisms by gluing, and similarly for the two morphisms. And if you sit down and scratch your head, you'll realize there's another way we could compose things. We could sort of take disjoint union. And that, categorically speaking, is called making it into a modular category. the two morphisms are, so I've got a two-dimensional cobordism from some collection of circles to some collection of circles, that's the one morphism. Here's another one morphism from the circle to the circle. And the two morphism is a cobordism between the cobordisms.
So it's got corners.
It's got corners. It's a three-manifold with corners, yes. But so, yes, there's quite a few technical issues there. You have to make very precise what you mean there. And everything what I'm saying here is resting on the thesis of Chris Schommer-Pries about 2 or 3 years ago. He was one of the collaborators, and he wrote down the details of this in his thesis. So yes, you have to take collars for your cobordisms, you have to take halos and everything to make sure that everything connects up smoothly. So yes, there's a lot of stuff from sweeping under the rug. Okay.
I don't understand the disjoint union combination. So if I had, say, a one cobordism.
Yeah.
A one morphism, sorry.
Yeah.
Two-dimensional.
I could say this is a one morphism from that collection of circles to that collection of circles. I could take out my pocket 3 other circles here, 1, 2, 3, put them in front of the board.
Yeah.
And take out my another pocket 5, 1, 2, 3, 4, 5.
Yeah.
And I could visualize some other one morphism going, yeah, cobordism from these 3 circles to that 5. So then I've got a way of taking one morphism and another one morphism in 2 completely unrelated things, stacking them together. That's what I mean by distributed tensor.
Right, so it's not, it's not a composition sense. If I go from A to B and then B
No,
to C, I don't get to A to
it's a
C.
composition in a perpendicular direction.
What do you think the other direction, A to B and
It's from A disjoint union A prime to B disjoint union B prime.
And this is part of the special structure of Mitchell.
Okay.
No, a monoidal two category. A two category, you can just compose things. So I didn't. You're right. You caught me. When I described two categories, I didn't mention the word monoidal there, but I should have. So you're right. There's in the two category. There's the direction of the one morphisms, and there's the direction of the two morphisms. In a monoidal two category, there's a third direction as well.
Okay. Alright. So then the answer
The monoid operator.
The one where we take disjoint union in that direction.
Alright. The answer to the question I thought I was asking. Okay.
So let's define an oriented 1, 2, 3 topological quantum field theory as a symmetric monoidal two factor from this bordism 2 category into the 2 category of linear categories. So, I mean, this is not what you would call an extended TQFT in the sense of Byers and Dolan, right? Because I should go all the way down to points. But that's why I've written here 1, 2, 3. So my objects on points, they close one manifolds. So I should be going all the way down, but if I did go all the way down, I'd be dealing with 3 categories here, which is kind of tricky. The only reason we do this is because we can at least make this precise. Okay. But going down to points is philosophically what we should be doing. It's just that it's technically quite tricky.
what's the new cat?
It's a 2 category where the objects are linear categories, like your favorite linear category, like it could be the representation category of an algebra or something like that. The only thing I require is that harm sets of vector spaces and that certain technical conditions like direct sums must exist and so on. Morphisms are linear functors. 2 morphisms are natural transformations. What's tensor product? If I've got a linear category A and a linear category B, I can take what's called the Deligne tensor product. I can construct a new category whose objects are are generated by the formal tensor products of each individual object, and the harm sets are the tensor products. So it's sort of like taking the tensor products of 2 vector space. You can take the tensor product of linear categories. And so we're just talking about a representation in there. So that means that to a circle, to the circle which is sitting in here, we're going to assign a category. To a cobordism between circles, we're going to assign functor between, say, 3 circles to 2 circles and so on. Okay, now, so in this talk I want to outline 2 theorems. One is to give an actual generators and relations description of this thing here. And then to use that generators and relations description to classify these such functions. So I want to show what are the building blocks you need to build cobordisms up to dimension 3, and what are the relations between them. Now, so I should at this point now define what it means to give a presentation for a symmetric monoidal 2 category. It's sort of these details again I'm stealing from Chris Schommer-Pries' thesis. So we all know how to take a bunch of elements and a bunch of relations and then give a presentation for a group. We go one level, a group can be thought of as a category with one object, right? The morphisms are the group elements. So by the same principle as for giving generators and relations to make a group, I can also give generators and relations to make a category. It's just a mini-object version of what you do when you have a presentation of a group. Everyone with me?
So you don't list all the objects. You give.
You would have to, if I would give a generation for a presentation for a category, I'd have to give you a list of generating morphisms and say, B goes to C is another one, and then I have to give some relations between them.
You don't have
G after F equals something else. Sorry?
How do you generate the objects?
Yeah, so that's a good question. At this level, I haven't yet talking about the monoidal thing yet. So I'm just talking about, I've gone from, psychologically, we've gone from happy with presentations of groups, now we're happy with presentations of ordinary categories. Okay, I'm just baby steps. Now imagine our categories got a tensor product operation, like a category of vector space, we can tensor things. Then it might be that every object is the tensor product of a whole bunch of simple objects or something, and then it allows me to simplify giving the generators. I just have to give some basic simple ones which will build everything up. And now I'm just going one level higher to a monoidal 2 category. Okay. You can write down what this means to give a presentation. Maybe I'll just skip over this because it's exactly what you think it is, essentially. But well, I mean that's belittling the work that goes in here. This is tremendously difficult to write down. This all explicitly takes a lot of effort. Okay, but the upshot that I want to get to is that essentially you give a bunch of objects, and then you say that every object is going to be a tensor product of those. You give a bunch of morphisms, and you say that every one morphism is going to be isomorphic to something that you can build up by taking disjoint union of composites of those already. And similarly with the 2 morphisms, but the thing I want to point out is that in this paradigm I'm outlining here, we're only going to allow relations at the level of the 2 morphisms. So we're going to only be allowed to be able to say that this 2 morphism equals that one. Because in sort of higher category theory, it's evil to speak about equations anything other than the topmost level.
So any relation amongst the one morphisms or objects should be implied by
yes.
relations.
Yes, you should never have a relation in the sense of an equation between the one morphisms. You should only have isomorphisms. You with me? Otherwise, you have abandoned the great philosophy of higher category theory. Only at the top level should you have equality. Okay. Say again. N is some
general number.
Yeah, it's the general, exactly. Okay, so there's a bunch of high categorical mumbo jumbo here. But here's the upshot, is that if you've got a presentation in this sense of this Bordism 2 category that I was talking about, then to give an oriented 1, 2, 3 topological quantum field theory is the same thing as to give a G-shaped object in the 2 category of linear categories satisfying the relations. Okay. So I can now just, to classify these, I just need to go and look at what the generators and relations are for this guy, and then just look at those shapes of diagrams in here.
G-shaped object is an axion object, or G-shaped object is a bunch of objects, morphisms?
Yeah, it's a bunch of objects, morphisms, and 2 morphisms.
Okay.
Yeah.
Object.
No, it's bunch of object morphisms and two morphisms satisfy various relations. And if you can find that in there, then you've got a TKT. Okay. Everyone who's really lost now? No. Feeling a bit uncomfortable. When am I going to get to the point? So when am I going to do something? Abstract nonsense up to now. Eh? Okay. I apologize for that, by the way. One of the horrible things about this field is that there is such a lot of abstract nonsense. But I assure you that I also want to calculate invariance of manifolds just like it. So your level of tolerance for this kind of stuff might be quite low, but yeah. It's not that I love this for its own sake. I also want to, calculate some. I want to class of maps and so on. Okay, so the first theorem on outline. Here I'll give this presentation for this cobordism 2 category. So we're saying here are the generators. So generating objects is a circle. That's obvious, right? Every circle is just a disjoint union. Every one manifold is a disjoint union of circles. Generating one morphisms are these guys here, and that's also obvious. Every oriented surface can be built up by gluing these guys together, disjoint unions of that. Generating two morphisms. Okay, so now there's a whole list of them, and they're split into two types: the invertible ones, invertible at the level of the two morphisms, and the non-invertible ones. So the invertible ones, these are going to be the things that present the mapping class group of the surfaces. So the first one is that we have a diffeomorphism from, so remember time's going up here, so pants with the cylinder to the cylinder and then pants the other way. It's called the associated diffeomorphism. And it's quite an obvious diffeomorphism, you just push up like that. And there's an inverse. By the way, these are diffeomorphisms, but we realize them as cobordisms. Because remember, a cobordism from A to B is a manifold together with explicit identifications of the ends. So to realize this, a diffeomorphism of the cobordism, I take that two manifold, then I cross it with the interval, and then I glue on this guy with the identity, and I glue on the other one with the diffeomorphism. So I can realize a diffeomorphism as a cobordism. And similarly, we've got these guys here. This one is quite an interesting one. It's a diffeomorphism from the pants to pants after a sort of switch map. And it is sort of the one which is the diffeomorphism which you'd realize by sort of taking this tube and moving it around like that. But it's important for structural reasons. Very important. It's called the braiding. There's a diffeomorphism of the cylinder, the Dane twist. Right? Let's concentrate on that. It's the Dane twist around the cylinder. And we've got some more interesting ones. We've got this guy here, which operates on the, if you like, the sphere with 4 punctures. And it's essentially just Dane twist around the central meridian there. That's what we call 2. And then this other one is the move which interchanges. This diffeomorphism 3 is the move which interchanges meridian and longitude. What's the name for this circle?
Longitude.
Longitude. Yeah. Okay. And at the bottom here, you've also got these Frobenius edges. So they're diffeomorphisms which sort of move that up and vice versa on this side. Okay, those are all the invertible ones. They generate the mapping class group. If you like, come to that. Up till that point, that was sort of known in the from about 2000s. People were thinking about things that way. One of the new ingredients that we're bringing in is we're insisting that you must also think about the non-invertible ones. Okay? So these are cobordisms which don't have an inverse. If I can do, this is a cobordism from 2 cylinders to copants after pants. If I do this cobordism and then that one, it's not diffeomorphic to the identity cobordism of the cylinders. Okay? And it's crucial, obviously, to build up 3 manifolds. You need these. And you can you get 4 types. This is the creation of a sphere, and cancellation of a sphere, and so on. It's a 3-dimensional manifold, and the way to visualize it is just to simply take slices. So over here, it looks like this, at time t equals 0, time t equals 0.2, a little part of this will come out. Time t equals 0.4, they'll get closer. Say t equals 0.5, there's a sort of singularity as those 2 points cut into each other. As a 3-dimensional manifold, at least with corners, it's perfectly smooth. But the slices might look singular. And eventually we end up with this.
And how should we think about the, well, I guess I was going to say the inverse, but there is no.
There is no inverse. Right?
Okay,
The opposite is just straight up.
It's just, yes, the opposite is right, the cobordism backwards. Time in reverse direction.
Oh,
the identity for it. Okay.
Yeah, the identity, yeah, that's right.
Alright.
Yeah. So those are the generators, right? So we're saying that every cobordism, in particular every 3 manifold can be built up. A 3 manifold can be thought of as a cobordism between the cobordisms which go from nothing to nothing. Okay. But we can also, we're saying in general, any cobordism between cobordisms can be built up from those. Then there's the relations, and these are living at the top level, right? We say that some composite of cobordisms equals some other composite of cobordisms. So there's first of all the relations between the purely invertible generators, such as this one. Okay, I'll start off with pants, then copants, then pants. I do a 2 move on this guy here, 2 diffeomorphisms to get there, and I do a 2 on here to get here. I do a 3 move on here to here, and I do a 2 move. Or that's the same as doing 3 Dane twisting around there twice, then a 2 on that and 3 on that. 2 is that move where you take copants off the pants and you move it, do a 360 rotation around like this.
It's a Dane twist.
Dane twist around
vertical
circle. Okay, so this is sort of like we're generating the mapping class group here, not just for the torus, but for all possible surfaces at the same time. That's the beauty of this high-dimensional algebra way of doing it. We're writing down a finite presentation for the mapping class group of all surfaces. It's not immediately obvious if you don't think about it. Not immediately obvious that that's possible if you don't think about things high-categorically. So this particular one should be compared with this relation in the mapping class group of the torus. Because S corresponds to 3, the S view on the torus, and T, which is the Dane twist, corresponds to 2 in a certain sense. Okay. So you get a whole bunch of those, right? I've just drawn one of them, and there's a whole bunch of them. And then you get a whole bunch of relations between the non-invertible generators. The most interesting to me are these ones here, right? So I told you that they're not invertible, but a certain composite of them does give the identity. Namely, I could start here, then I could do the eta move. Remember that sort of glues those 2 pads together, so that glues them together to get this. And I can do an epsilon, which would get rid of that hole there, go back to the copants, and that's the same as the identity cobordism from there to there.
It's a cancelling 1-2.
Yeah, it's a cancelling 1-2 handle. Okay, exactly. And this is also a cancelling 1-2 handle. So those are just the Morse relations. But the reason why I like them is because categorically speaking, these are exactly what's called an adjunction between pants and copants. So what we're seeing here is that, I don't know if I wrote this down. No, but we're seeing here a very precise dictionary between Morse theory and high-dimensional algebra. Something which is nice at the level of Morse theory, cancellation, translates into something very fundamental at the level of category theory, adjunctions.
By the way, I think there's last picture on the bottom row that's upside
Yeah,
down.
you're right. That's it. That's the upside down. So this should be.
Which one's upside down?
I think this.
The
The last one's upside down.
Because it's not the identity, it's not going.
Yeah, exactly. Thanks. And so the proof uses surf theory methods from Chris Schommer-Pries' thesis, and I'm going to try and outline it now. And one of the reasons I came here was to learn from David how to understand what on earth is going on here. Okay, so I've learned quite a lot being here, and I really appreciate that. So this is not my level of expertise in this program. I'm sort of more, once you've got the presentation, how to then characterize what's going on the categorical side. But I really need to understand this side of things more. So I'm going to try and speak a little bit about that.
And so the fact that those are relations is just simple topology, right?
So that's simple topology.
But the fact that
they're enough, yes. And even that your generators are enough.
Yeah.
I don't know that there aren't some weird diffeomorphisms I can't get, and so on, or weird code. I mean, we say we can build all possible 3 manifolds by these things, and you can recognize 2 different 3 manifolds. The 2 manifolds are different, precisely different under these relations, right? Okay. So let me try and outline it. So how do we do it? So first of all, we need to go and use a basic theorem, the classification of oriented 1 manifolds. Okay. And we need that from God, basically. We can't do anything about it, but luckily that's easy. But that's an important point, because if I was doing the 4, 5, 6 topological bounded field theories, I'd be in trouble. Okay, so that's why we're sort of just in that part where it is doable. Then the ordinary Morse theory for the 2-dimensional cobordisms, which are the 1 morphisms in this 2 category, gives us the generating 1 morphisms. Ordinary Morse theory tells us that there's 3 kinds of index critical points that can occur, 2, 1, and 0. And yeah, I've distinguished the pans from the copans, even though they're both at index 1. So ordinary Morse theory wouldn't really distinguish them. But they could be distinguished by saying that at least the index doesn't distinguish them, but the fact that over here the fiber is a circle and below 1 the fiber is 2 circles distinguishes them. So the Morse function itself just does distinguish. Then we need sort of a 2-dimensional Morse theory, categorified Morse theory for 3-dimensional cobordisms gives us the generating 2 morphisms. Okay, so that's where we take functions from our 3-dimensional manifold M into R2, and then we also bear in mind that we can compose with the projection map into R to give us an ordinary Morse function of our 3-dimensional manifold. We will come to that now. But if you study the singularities of maps into R2, then it's known exactly what they look like. You basically get certain singularities, and because I'm remembering the post-composition into R, we get 4 kinds: fold singularities, cup singularities, Morse singularities, and crossing singularities. Okay. In fold singularities, the cobordism is isomorphic to the identity. So this is just where the critical point, the time's going like in this direction now. The critical point starts up over there, and then it might move around, so someone might move this up and down a little bit, and end up where he started. So the locus of the image of the singular point traces out a fold. And that, but we have to be careful there because there could be a snake or a cat in the grass here. So we have a movie here. There's a cat waiting for in the grass. Oh. Okay, so the problem is that you might have such a singularity graphic, even though the cobordism is non-trivial. So for example, a Dane twist is like that. There's no singular points in this Dane twist. They're just smoothly rotated around. And the singularity graphic would just look sort of like a smooth curve, even maybe go directly horizontal. But it still encodes a non-trivial cobordism, so we have to be on the lookout for problems like that. And this is one of the reasons why classifying 1, 2, 3 TQTs is in a certain sense more difficult than the fully local situation, going all the way down to a point. This would be easier. Only trouble is then you have to deal with symmetric monodal 3 categories, which is algebraically more difficult. Topologically easier though. Okay. So I've described the fold. Then the next thing that can happen when you've got a map from a 3-dimensional manifold into R2 is you could have a cusp. This is handle cancellation. I start off with the critical point of index 0 and the critical point of index 1. It's the critical point of index 0, the increasing manifold is 2-dimensional. Index 1, and they move down, and they meet. I get a cylinder, that gives me a cusp. And there's also one which goes the other way. That creates a 0, index 0 and index 1 critical point. And I've called that lambda inverse for sort of pretty obvious reasons. Later on we're going to see that lambda inverse after lambda equals the identity. So far we can't yet conclude that. This is simply just some cobordism we've come up with. We've not got to the relation stage yet, just making the generators. Okay. For more singularities, a handle attachment in the time direction occurs. For me, yeah, time is running to the right. Okay. So, for example, I could have index 0 and index 2 critical point come together. And this going in this direction here, I would say that that is a Morse singularity of index. You're attaching a one handle. Yeah. Okay. No, if I didn't post-compose with that map into R, I wouldn't have these things. But so that's why it's slightly different to the normal classification of singularities and maps into R2. Let's look at another random one here. Yeah, I've got nothing, and then these two cylinders come together, boop, and they form two index 1 critical points, which then move apart. We'll get to here. Okay. And these are all the possible things that could occur. Everyone happy? Okay. You can also, in crossing singularities, a diffeomorphism occurs. So to go from here to here, those index 1 critical points swap places. Similarly for those other diffeomorphisms. So I'm building up the generators now. But I have to be honest, and there's a lot of this stuff that I don't understand yet. David's helping me. Some of these guys, it's not so clear to me what's going on. But that's how we get the generators. Now to get the relations, we need surf theory, a three-dimensional surf theory. So we now have a map on manifold R3, and we also remember the composites projections into R2 and R. So we think of these as allowable moving moves. Okay. What do I mean by that? I mean there's a certain singularity whose the locus of the singularity is living in 3 dimensions, but I'm not going to draw it in 3 dimensions. I'm just going to draw the slices in. And so this is a slice in the beginning, this is a slice at the end. So you must imagine that there's a development of this into that, and that's where you get that familiar sort of cusp and terminus page. Each of these guys corresponds to a cobordism, and so this, to say that I can go from here to here, means that I can move the function in the space of all Morse functions from there to there, and therefore they must be diffeomorphic as 3-dimensional cobordisms. So this gives me an equality at the level of cobordisms. So in this one here, I've created nothing's happened. I've got an index 1 critical point, which is that guy there. Time goes across here, and at some point over here, I've now created 2 index 1 critical points over here. So these two here have been created. And then they get cancelled. So I go here, these two get created, then these two cancel off, and I'm left with that one. That composite of cobordisms is equal to this composite of cobordisms, so nothing happens. Or at least diffeomorphic to it, because I can smoothly go from here to here in the spaceable functions. So this gives me an equation at the level of two morphisms. It gives me my relation. I get this one, and running time backward, I get the other one. And categorically, these are exactly the statements that this one morphism here is the adjoint of that one morphism there. So if you like adjoints, then Morse theory and adjoints go hand in hand. And you also get similar ones for copads and coupled for cap. Then we get the cusp inversion singularities. And this is a movie move which goes from this movie, from this, it's a movie of singularities. In the beginning, the singularity graphic looks like this, so that outlines a certain composite of cobordisms, and at the end it looks like that. So over here, I've got an index 0 and index 1 critical point. Just looking at that time starts there. This line here corresponds to this whole picture, this line. And then you see this, the 0 and the 1 come together, and at some point a cancellation occurs, somewhere exactly over here. And in the middle here, I've just got a cylinder. And I move on, and it sort of pulls out again, go back to where I started. That gives me a composite of cobordisms. And the surf theory says that in the space of Morse functions, you can make a path from this to that. And so that a path going from here to here gives me an equation in my category saying that this composite is equal to this composite. This is just the identity one. Running it the other way around gives me a different. Running it the other way around gives me a different equation between different things. So it's a little bit strange. But I'm counting equations, not singularities. And then there's another one that could happen. I could create pair cancelling points come together again. And that would be saying that this composite equals that. So all in all, this is simply telling me that at the level of algebra, lambda inverse really is the inverse of lambda. Okay. So that's what the cusp conversion singularities do. The swallowtail singularities tell you something else. Right? You can have crossing and then a cusp, and then a cusp on the other side. Running out of time here, so I'm going quite fast, but you can get some equations like this as well. This is another kind of singularity that can occur. Remember what we're doing? We're looking at all the possible singularities that you can get when you have a map from M into R3. Swallowtail is one of them. And if you look at everything that can occur here, you get 12 of these equations. So I'm really building up a whole bunch of equations, right? The Morse guys alone gave me 8. The cusp gave me 6 equations. Swallowtail gives me 12. And it doesn't end there. There's a whole bunch more, sadly. Okay. I haven't talked about the double crossing. That's even more elementary. This sort of just says that those diffeomorphisms that I was talking about, like alpha inverse, then it's saying that alpha inverse really is the inverse of alpha. So I've spoken about the Morse ones. There's 8 of those equations. Categorically, they correspond to adjunction equations. The cusp inversion gives you 8 equations. Categorically means inverses. Swallowtail gives you 12 equations, and now the type 3 equals 1, meaning some composite of 3 things equals some other thing. Those aren't all the singularities that can occur. There's other more important ones, like cusp flip. It's going to use another singularity in 3 dimensions. This gives you 4 equations. Another one called beat to beat. Okay. David, you're nodding your head, but who else is familiar with these singularities?
I thought beat to beat was that one where 2 cusps cancel each other. I mean, that's like an old singularity.
Yeah, I am doing good old-fashioned singularity. Isn't this 2 cusps?
It's the cusp conversion.
Oh, is it? Like maybe I've said it wrong. This might be called lips.
That word too. Oh, no, lips is the inverse of beat to beat. Of what I was called.
I think that's just sometimes it's called beat moves or something. I don't know.
Okay.
Yeah, beat.
Okay.
What?
The beak move. That's a set.
There's only one.
Yeah.
And yeah, you can see, you just look at these singularities, each singularity gives you an equation. And we're getting huge amounts, so 20 equations, 10 of these. Each of these is a hexagon, saying some concept of 3 things, some concept of another 3 things. So categorically, things are getting quite complex. The sad fact is that there's still even a few more equations having to do with the action of the mapping class group, which hasn't been entirely accounted for in what you've said there. Okay. But nevertheless, the good news is that, well, it all, you can write it down, and then you can at least write down the equation. That gives you a presentation for the 2 categories. Okay, so now using the presentation, you can classify these 1, 2, 3 TQFTs. So the theorem there is that, so I've just got 1 or 2 minutes left. If you've got a TQFT, what kind of data do you get out? So remember, it's got to a circle, it's got to assign a linear category. Okay, it turns out that we're going to get a whole bunch, from all the other structure, we're going to get a whole bunch of other structure on this linear category, and that's going to completely classify this functor. Namely, the structure you're going to get on the linear category is what's called a modular category. It's a kind of category where you can tensor things together, you can braid things around, there's a twist, and there's duals in a certain sense. So the statement is that such a function is completely classified by the thing that the circle gets assigned to, the linear category that the circle gets assigned to. So I need to go in 2 directions here. So going from a TQFT to a modular tensor category uses directly the presentation. And the rigidity follows, this is a new point from invertibility of the Frobenius data. So buzzwords there, but I would mention that because it's something that people were always confused about before. Going the reverse, going from a TQFT, so from modular category to TQFT, you basically have to check, so you can construct a TQFT, now you have to check that it satisfies all the relations. And to do that, we sort of came up with this sort of new way of doing these calculations, which we call internal string diagrams. And these are what they look like. You sort of draw diagrams which live inside your cobordisms. Okay? And you can make certain moves that these diagrams that are allowed, which correspond precisely to the relations. And then you can, in checking the relations amounts to checking that if you go one way around, going the other way around, that you get isotopic things at the end of the day. Okay, so it's sort of, it's quite a nice calculus. You might have heard about this kind of stuff before, like wasn't this all done in the 90s? Okay. And that is true in a certain sense. A lot of these ideas date way back, as we've seen. But what is actually new in the stuff I'm talking about? Firstly, we have a full finite presentation of this 2 categories. Various people have done various versions of this, but not the full-on case like we're doing. Except even ours is not the full-on case. As I say, we should be going down to 0, and we should, if we want to make contact with the great philosophy, we should be talking about the framed cobordisms. That's framed cobordisms is what higher dimensional algebra is really all about, not just orientation. Okay. So there's some other stuff that I wrote down here, which sort of just demonstrates how we differ from what was already known. Okay, thanks.
So, really simple one. If you knew what a TQFT was supposed to be, and you knew, then you're saying that once you've decided what modular tensor category is assigned to the circle, everything else.
Yeah.
Any modular tensor category is assigned to a circle will work.
Yeah.
And then
yes.
it will generate a functor.
Yes.
And
the data of such a 3D TQFT is precisely encoded in the data of modular tensor category.
So you pick your favorite modular tensor category, assign that in a circle, and compute.
Yeah.
And it gives you an invariant of
the 3 manifolds. Yes.
with boundary or
gives you invariant of 3 manifolds and 3-dimensional cobordism math. So it's richer than just an invariant of closed 3 manifolds. But I mean, this is just abstract nonsense. I mean, unless I can give you some explicit examples of modular categories. So what I should really be doing is saying, look, here's how you can build such data. You can take you take your favorite finite group, you take your favorite 3 cosine of a finite group. You can build such a thing, and so on. So yeah. If it just stops here, it's just empty nonsense. You have to actually build an invariant of manifolds from some data. You can't just.
And to do 2, 3, 4, where does the program get hung up?
You shouldn't. You should. To do 2, 3, 4 would get hung up already. You wouldn't want to do that. You should go 0, 1, 2, 3, right? But
I mean, we still have classification of surfaces, so we do.
And 3.
We don't get hung up on the first point.
we get hung up on this point.
Yeah.
Won't we?
I see.
What are all the possible?
I see.
Yeah. And we'll get hung up. We'll get hung up on the next point. We won't get a finite presentation of this ugly.
Okay, thanks.
Okay. Thanks a lot.